Okay, we're going to talk about lesson 5.3, and it's on solving trigonometric equations. So we're solving equations, we're solving for x, but we have some tangent functions. We're going to solve trig equations using algebraic techniques and solve trig equations using basic identities. Here's a good hint for you. You might want to get your unit circle out because that could be really helpful here in figuring out what the angles are going to be. So for my first problem, I want to treat tangent like it's any other variable. Let's say it were y. So I'd get my variable terms on one side and my constant terms, those without variables, on the other side. So I'm going to subtract tan x. And that's going to give me 2x minus 1 tan x is just 1 tan x. And then I want to add square root of 3. And I get tan of x equals the square root of 3. I still want to find out what x is. So to do that, this is where we get to do the inverse tangent. So to get x, I'm going to do the inverse tan of negative, or the inverse tan of square root of 3. Now, tangent has a period of pi units. So I'm going to give values of x that are greater than or equal to 0 and less than pi. That's the values that I'm going to use, so that I don't have any repeaters. Because I could have multiple values that have square root of 3. If I use my unit circle, I'm going to get that when the tangent is square root of 3, x has to be pi over 3. Now I could go around my unit circle and find other values where tangent is square root of 3, but that's the only value in the range from 0 to pi. I'm going to do the similar kind of thing for my next problem. Again, I want to treat my function like it's a variable. It says solve by taking the square root of each side. So first I'm going to get the variable by itself. So the original problem is 4 sine squared x plus 1 equals 4. I'm going to subtract 1. That's 4 sine squared x equals 3. Then we're going to divide by 4 on both sides. Sine squared x equals 3/4. And this is where the square root part comes into play. I'm going to take the square root of both sides. And that gives me sine x equals, and I'm taking the square root, so that's going to give me a plus or minus. And when you have the square root of a fraction, you do the square root of the numerator and also the denominator. So 3 would stay under the radical, but the square root of 4 is 2. So I'm looking for values this time, because sine has a period of 2 pi, I'm going to look for values where x is greater than or equal to 0 and less than 2 pi. So I'm going to focus on the entire unit circle for this. And if I go around and I look at the unit circle, I want to know where sine, which is our y values, are positive or negative square root of 3 over 2. So sine inverse of plus or minus square root of 3 over 2. But really, I just want to know where y is square root of 3 over 2, either plus or minus. And I come up with pi over 3 at 2 pi over 3, at 4 pi over 3, and at 5 pi over 3, where x is greater than or equal to 0 and less than 2 pi. So I had you can have multiple values. Right, the next page, example 3 says solve by factoring, find all solutions of each equation in the interval from 0 to 2 pi. So we don't want to go anywhere past that. What I want to do first is I want to bring everything to one side of the equal sign. I've got cosine x, sine x, and then minus 3 cosine x equals 0. I'm going to factor out a common term, or a common factor from each term, which both of the terms have a cosine. When I factor out a cosine, I get sine x minus 3. Just like when we factor in algebra, which this is algebra as well here, when we factor in algebra, we take each factor and we set it equal to 0 then. So I've got cosine x equals 0 and sine x minus 3 equals 0. So let's focus on the cosine x first. That would be cosine is the inverse cosine, or x is the inverse cosine of 0. So I'm just looking on my unit circle, where is cosine 0? And that's our x coordinate. My values there, when we have an x coordinate of 0, is that x would be pi over 2 and 3 pi over 2. Then for the sine x minus 3 equals 0, I get sine x equals 3. And I don't have anywhere where the sine is 3. It doesn't go above 1. And if I put this in my calculator, I wouldn't get a value either because there's no solution here. So my only answers then are x is pi over 2 and 3 pi over 2. In part B, I'm also going to do some factoring, but I'm not going to factor out a common monomial. And I've got a little trick for this as well. I see that I've got a fourth term, I've got a squared, I've got a minus 2. I'm going to, just temporarily, I'm going to let y equal my cosine x. And so everywhere in the problem that I see cosine, I'm going to put a y. So that this would be y to the fourth plus y to the second minus 2 equals 0. Now I have something that just looks like a big polynomial to factor. So I'm going to treat this like a quadratic, even though it's not, but it's got some similar properties, because y squared times y squared is y to the fourth. And then I do have 3 terms, just like I'd have any other trinomial. I want factors of negative 2 that when I add them together give me 1. So that would be plus 2 and minus 1. And you can double check if you did the FOIL method. Y squared times y squared is y to the fourth. And then we've got y squared times negative 1 is negative 1y. Then plus, or negative 1y squared plus 2y squared would be y squared. And then the last terms would give me negative 2. So that works out. The thing with these to the fourth power is that you have to factor more than once. Y squared plus 2 cannot be factored again, so I'm going to leave that. But y squared minus 1 is a difference of squares. And when I factor difference of squares, I'm going to get 2 binomials. And in this case, one's going to say y minus 1, and one's going to say y plus 1. Now I have 3 factors, and I'm going to set them all equal to 0. And then solve. So I have y squared equals negative 2. But when I go to take the square root, I have the square root of a negative. So there's no, I can't do that. There's no real solution for that one. So I go to the next one. This gives me y equals 1. That's possible. And this one gives me y equals negative 1. Now I'm going to go back up to the top here. And where I had originally let y equal cosine x, I'm going to go back and I'm going to replace all my y's with the original cosine x now. So that I get cosine x equals 1 and cosine x equals negative 1. So I get on my unit circle and I look where I have a cosine of 1 and a cosine of negative 1. Both of those are x coordinates. I have a cosine at 1 when x is 0. and I have a cosine of -1 when x is pi. So those are my two solutions there. You can have a couple more here. This one says solve by writing using a single trig function. So I can see that I actually have cosine and sine. So I'm wanting to replace one of these two functions, either cosine or sine, with another function so that I have all the same. Either it's all sines or all cosines in this case. Well, the only thing I'm really going to be able to replace is this cosine squared because I have the Pythagorean identity. And my Pythagorean identity says sine squared x plus cosine squared x equals 1. So I'm going to solve for cosine squared. I get, and that means subtracting sine squared. So cosine squared x is equal to 1 minus sine squared. Where I see the cosine squared, I'm going to replace it with 1 minus sine squared. And then write the rest of your equation. And I want to do a little simplifying here, so I'm going to distribute. That gives me 2 minus 2 sine squared x minus sine of x minus 1 equals 0. And then I'm going to try to get it down, combine some like terms here. My negative, or my 2 and my -1, that would give me -2 sine squared x minus sine x plus 1 equals 0. Now, I don't like it that I have a coefficient on my leading term there of a negative, so I'm going to take everything to the opposite side. Just basically the symmetric property across the equal sign. If I do that, or if I can also think about multiplying everything by a -1, that's 2 sine squared x plus sine x minus 1 equals 0. I'm going to do the same trick that I did in the other problem where I replaced cosine with y. And let's replace sine with y this time. So that's going to give me 2y squared plus y minus 1 equals 0. Now I have something that looks a little bit easier to factor. You could use the quadratic formula if you wanted to. I'm just going to factor like normal because my leading coefficient is a prime number, so I know the only way I'm going to get 2y squared is to do 2y and y. And then the only way to get a -1 is for one to be a positive and one to be a negative. I'm going to make this +1 and this -1, and that'll allow me, for when I do the FOIL method, that would give me 2y minus y, which is positive y. All right, I'm going to take that then, and I'm going to set each factor equal to 0, so that's 2y minus 1 equals 0. And then I can solve that for y. I get 2y equals 1, and y equals 1/2. Now remember, y is still sine, so we're not quite done yet. And then the other one, I get y plus 1 equals 0, so y equals -1. Now you can go back and replace put the sign back in where you have the y. Sine x equals 1/2, and sine x equals 1. So I'm wanting to know on the unit circle, where does the sine of x equal 1/2? Well, that happens when x is pi over 6, and also at 5 pi over 6. And where sine is 1, I'm sorry, -1, that's what it should say. Where sine is -1 happens at 3 pi over 2. So those are all of my values there in the unit circle. And then finally, we've got example 6. It says solve by squaring. So I have cosecant x minus cotan x equals 1. I am going to change these guys to sine and cosine. That's going to make me feel a little more comfortable. So cosecant is 1 over sine x, and cotangent is cosine x over sine x. And so when I combine like terms here on the left, I get 1 minus cosine x over sine x equals 1. Then what I'm going to do is I'm going to multiply by sine x on both sides. Just get that out of the denominator. So on the left side, the sides are gone. I get 1 minus cosine x equals sine x. And then I'm going to square it. Now I get to the square both sides. On the left, if I did the FOIL method, that would be 1 minus 2 cosine x plus cosine squared. And then on the right side is sine squared x. I am going to use my Pythagorean identity again with the sine and cosine because I really can't solve these unless they're both have the same function. I know that sine squared x plus cosine squared x is equal to 1. So sine squared x equals 1 minus cosine squared. So I can replace this sine x here with 1 minus cosine squared in the problem. And then that way everything's in terms of cosine. Then, because I have a squared term, I'm going to bring everything over to one side. So I'm going to bring the 1 over and the cosine squared over, which that's going to give me 2 minus 2 cosine x, and then plus 2 cosine squared x equals 0. Now, for me, I like my squared term to come first, so I'm going to flip-flop things around a little bit and put 2 cosine squared x minus hang on, I wrote something down wrong. Let's back it up just a second. When I bring the 1 over, it's going to end up being 1 minus 1, which that eliminates the 1. Now I've got 2 cosine x plus 2 cosine squared x equals 0. And I'm going to, really doesn't, at this point, doesn't really matter if I flip-flop it around, I don't feel like. I'm just going to take out a greatest common factor of 2 cosine x, which leaves me with excuse me. Once you factor it, you're going to take each factor and set it equal to 0. So I end up with cosine x equals 0. We want to know where cosine x is 0. And that happens at pi over 2 and 3 pi over 2. And then for this guy, we're going to subtract 1. We want to know where cosine of x is negative 1. And that happens at pi. So there are my solutions.